Thank you for the kind introduction. Before I directly want to come to the Pirani chip that we developed, I want to have a quick view on the theory. So Pirani sensors are basically small thermal miniaturized or sometimes miniaturized sensors which measure the thermal conductivity of a residual gas in a vacuum system in order to detect or measure the pressure or the vacuum level that we have in our vacuum system. The thermal conductivity of the gas can be described by the thermal conductance, which is just a measure for the thermal conductivity. But beside of the thermal conductance of the gas, we have other thermal losses of our hot membrane, such as the radiation. Because of the black body radiation, we lose temperature on our membrane, but we have also thermal conductivity over the suspensions of our membrane. Basically, there's also convection, but since we are in vacuum, we can neglect it because it's so small that we can't really see it. When we measure now, we can only measure all of the three thermal conductances as a whole. So we can only measure the one which describes the sensor at its own, and we can also have a schematic view how a measurement of this looks like. So we can only measure the yellow curve. This is separated from the parasitic thermal conductance, which is constant over the whole pressure range because it's independent of the pressure. But different to that, the thermal conductance of the gas depends strongly on the pressure, at least for vacuum. When we go to higher pressure, so it's the atmospheric pressure is somewhere around here. When we go upwards, it's nearly stable, but when we go to vacuum, it goes towards zero. So because of that, we have two saturation points at a low pressure. We basically just measure the parasitic effects, and at a high pressure, we measure everything, but everything stays constant, so there's no difference anymore. By calculating the slope of our curve now, we can determine the measuring range between the minimal pressure and the maximum pressure. And this is defined by the resolution limit that we have in our measurement system, but also by the noise level, which reacts quite similar to the resolution limit. So basically, there's one point where we can't even differentiate between pressure change or not. Usually, the measuring range is from 10 to the power of -4 millibar up to several hundred millibars or even atmospheric pressure. Langer has derived in his theoretical study of an equation to describe the norm sensitivity of a Pirani sensors in constant temperature mode. I don't want to go into detail of this equation, but basically we have some influences like geometry, which is described by the area of our sensor element and the distance between the sensor element and the heatsink. Then we have some effects of the residual gas. So depending on which gas we have inside of our chamber, we have different sensitivity or basically different behavior of our sensor. So this is described by this epsilon and the gamma, and of course the pressure has an effect on the output of our sensor. Now we can play a bit with these values, like the ratio A divided by GTHP, and we can also vary the distance between our sensor element and the heatsink. When we just change the distance between sensor element and heatsink, we see that the norm sensitivity moves to the left when we increase it or moves to the right when we decrease it. This just that's interesting, but it doesn't really help us because we lose quite a good part of the measuring range in the high pressures, and we also want to measure there, so it does not really help us. But when we look at the ratio, we can increase the whole ratio. This can be done just by increasing the area of our membrane, or we decrease our parasitic losses. The membrane can't be increased. There's a certain limit because we have to fabricate it. The membranes are usually quite thin and they will break once you have a certain area. That's why we concentrated on limiting or reducing the parasitic losses over the suspensions. And this is how we came to additional heaters on the suspensions. They work as counter heaters to limit the thermal losses over the suspensions. And yeah, then we can reduce it and we increase the measuring range towards lower pressures. But at the same time, we increase the sensitivity also at lower pressures. So this is how our sensor looks like. It's made on a silicon wafer with a chip size of 5.85 times 4.8 millimeters. The chip has free-floating membrane, which is only suspended on the four corners. And next to it, we have a reference structure. The membrane is under-edged, so it's free-floating and only suspended. And the reference structures is directly coupled to the substrate, so they are meant to compensate for changes in the ambient temperature. However, at the current status, we did not use the reference structures and did only measure with the membrane itself. The membrane has a size of 2.2 times 2.2 millimeters. And the special thing of this chip, we have on the suspensions additional heaters, like you can see on the detailed view there. All of them are connected in series, and we can contact them independently of the membrane itself. So we can control both temperatures independently. The membrane itself is held at constant temperature, so therefore we used a self-balancing Wheatstone bridge. The RM is the resistance or the heating structure of our membrane, and the R5 is just a potentiometer to adjust the temperature. During operation, we set a temperature of 125 degrees. This results in a temperature difference between a sensing element and heatsink of about 100 Kelvin. It's just to have good difference. And the voltage that we apply on the Wheatstone bridge is our measurement signal. This is acquired with a National Instrument data acquisition system with 16-bit of resolution. Since the sensor is not yet compensated for changes in the ambient temperature, it's quite hard to compare measurements taken in sequence. That's why we just built up the whole system twice and connected to the same flange of our vacuum chamber. So both of them face each other, they see the same temperature fluctuations, and they are at the same pressure. As a reference sensor, we use a Thyracont sensor. That's our project partner. This is a combination of a conventional Pirani sensor in combination with an ionization vacuum gauge to measure at even lower pressures. Additionally, we have a venting valve, which can be set quite accurately to vent the chamber with nitrogen. And on the bottom, we have some vacuum pumps to pump down. At first, we did a comparison to check if both sensors behave the same. We can already see during the sweep, one line lies above the other, so they behave the same. When we now calculate the sensitivity of both sensors, we can also see they overlap each other, so we can take them as a comparison. During this measurements, the suspensions of both sensors stayed unheated. So it was just a sensor as it was a usual Pirani sensor. Then at the next test we had we used sensor 1 with heated suspensions, therefore we just applied 3 volts on the suspension heaters. This is the maximum voltage at which the temperature control stayed stable. So this means the set point of 125 degrees on the membrane was still set and we did not go above that. And sensor 2 stayed as with unheated suspension heaters, and yeah, it was as in the measurement before. And we can already see at low pressures there's quite a big difference. We need a smaller voltage to reach the set temperature. And yeah, now we can again calculate the sensitivity of our sensor, and we already see, as the theory says, at high pressures the sensitivity behaves the same, and at low pressures there's a difference. The sensitivity is increased with the use of the heated suspensions. But since we have some noise issues at the lowest pressures that we have, this is because there are some pressure fluctuations between our reference sensor and our samples under test. But at the same time, due to the double logarithmic view, even small changes have quite a strong effect, which makes it appear worse than it basically is. Thus, we made another view. We just used the lowest, the measured voltage at the lowest pressures and subtracted that from each single measurement point over the whole measurements. This causes these two curves moving to the x-axis, and this enables a double logarithmic view of the blank of each single point or measurement point. And then we, by adding the average noise level over the whole measurement, we can define the lowest possible pressure where we can measure. Yeah, so we can see there's approximately a difference of 1 order of magnitude. So we reach about 3 times 10 to the power of minus 6 millibar, whereas we have with unheated suspensions 3 times 10 to the power of minus 5 millibar. So then I come to my conclusion. The active heat loss compensation improves the performance of the sensor. This means the sensitivity was increased for low pressure regimes, and at the same time we increase the measurement range by approximately 1 order of magnitude. If you're further interested in this sensor, you can also scan this QR code to come to the paper we wrote for this conference, and thank you for your attention.